Welcome back. Now let's look at the solution of this problem. So we've seen this expression for the number of cells in one cluster. And we know that our signal to interference ratio, we know the value for this, we know the path loss exponent, and then we can solve and we find that n is a reasonable value. Based on that, we can compute the user capacity. So recall that this is NC, this is the number of active users per cell, is the total bandwidth over the user bandwidth times the reuse factor n, and then you find that this is equal to 20 by plugging in the values. Finally, the system capacity is given here by bandwidth over the cell size squared times n times bs. Plugging in those values, you find 0.02. Okay, so we have a very small number of users per square meter, right? If we want to increase this, the number of users per square meter to 1, right? The only way that we can do this is to have much smaller cells. So we can solve for the cell size, and we find that we need cells that are about 20 to 25 meters in size. The last topic we will see today is something called power control. And this is another way of using signal to interference noise ratio, the concept of that, to improve performance. So here is an example with two base stations. And as we've seen before, that it's possible when the two users are assigned the same, for instance, time slots in TDMA, that they will mutually interfere with each other. So when you have higher transmit power on a link, you of course will have better performance because you can be protected against fading. You'll have higher SNR, so this means lower bit error rate. And then you can use link adaptation to transmit at a higher rate when the channel is good. On the other hand, this leads to more power consumption. And also it leads to more interference to other users that you're using the same frequency band or the same time slots. So for that reason, it is not meaningful to push the SNR to as high a level as possible. Instead, we will have an SINR target value. Right, so when the SINR is above some value, we are happy, but if it gets larger, we don't become more happy. But when the SNR is below that value, the system doesn't work. And this is a way to adjust the transmit power to just meet this SINR constraint. So in this context, we say that the packet reception is successful when the SINR is above some threshold. So this here is the threshold, and even different users could have different thresholds. So this equation refers to this scenario where we have a base station and multiple users. Each of the users will have a certain channel gain, so that's gain from the user to the base station. Let me see again here, what is I? I is the base station. I is the base station index, and then J is the user index. Okay, so there's a certain channel from the base station, from the user to the base station. This is called GII, so let's say this is base station 1, UE1 is the intended user. PI is the power that this user is using. So this is the signal power. Then we have the interference and noise power. Here nu I is the noise power, and this is the interference power. So this is the interference due to all the other users that are using the same resource. Okay, so this could be users that are, for instance, being assigned the same time slot or the same frequency band as the intended user. And then this will be their interference. And you see that this interference depends on the channel from those users to the base station, as well as the powers that they use. If they use 0 power, then there's no interference. And now the optimal transmit power should satisfy this constraint, because it doesn't make sense to use more power than to exactly satisfy this constraint, because when you use more power, you will create more interference for other users. Okay, so you should satisfy this with equality. So consider now this example here with 2 users and 2 base stations. Okay, base station 1 and 2, user 1 and 2. So let's see here, UE1, base station 1, UE2, base station 2. So write down the SANR expressions for each of the links, and there are 4 links, right? 2 desired links and 2 interfering links. And given that, can you then make a plot as a function of the powers to indicate which powers would be optimal? So you can pause the video and try to solve this problem and then get back. Okay, so the solution is maybe a little bit involved. So here on the top right, we have the scenario where we have the users on the bottom and the base stations on the top. We have the desired links and the interfering links. And then for each user, we need to decide a certain power, P1 and P2. Once we decide a certain power, then we can compute the SINR on each of the links. So this is the SINR on the link from user 1 to base station 1 is the desired signal plus the interfering signal. So let me try to draw this in green. This will be this part. For user 2, we have the desired link. Okay, this is this one. The noise and the interference. And then the interference I draw like this. So this is the interference. And we want to make sure that both of these constraints are met, so that both users are happy. Now, this first expression here, we can rewrite it. So let me highlight the expression now. This expression here, we can express it equivalently as this. Right? And this is an expression that's linear in P1 and P2. So any powers that satisfy this expression are good from the point of view of the first user. And what I'm plotting here are the different powers, P1 and P2. In order to satisfy this expression, okay, this determines a region. Okay. And anywhere on this side of the region, okay, here, user 1 is happy. Right? Because for user 1, you've met his SINR constraint. Okay, so this is user 1, this is for user 2. For user 2, you have this expression, so user 2 needs this to be satisfied. Let me again try to write this in a color. So here, I can rewrite this expression with this equation. Okay, that's exactly the same expression, which is now linear in A1 and A2. And this tells me that user 2 is happy only in this region. Okay, so here, user 2 is happy. And again, it is happy because it meets its SINR constraint. So then in total, for user 1 and user 2 to be happy, you need to be inside of this gray box. So any value here, inside of this gray box, user 1 and user 2 are happy. Fine, but now if we look inside of this region, there's an infinitely large region. So I could choose a power, let's say here. But also a power here will be good. Power here will be good. So which is the best combination of powers is actually this point. Because this is the power that is overall the smallest. Right? There's no total power that is smaller than this one. So this is the optimal point because it minimizes the energy consumption. Okay, so any other selection of powers will lead to a total power that is more while still making both of the users happy. And you will find this point by looking at the intersection of these two lines. Okay. So this is how we can solve this for this 2-user case. It turns out that for the more general case with multiple users, multiple base stations, there exists an elegant solution which is called by this name, which you can prove leads to the optimal power allocation for multiple users and multiple base stations. So the condition that needs to be satisfied is this one. This is the SINR condition for the different users. And this is the solution to the algorithm where user I at iteration n+1 adjust its power based on the previous power, and here a metric that relates to the interference. And by doing this, you find an optimal solution that satisfies all of this with equality, and this turns out to be completely distributed. So most of the lecture we've been talking about cellular communication, but there are also other communication systems such as Wi-Fi which use random access. So in this case there is no central coordinator, but it's basically every node is up for themselves. They have to fight to compete for the channel. And this is typically the case where you have many more users than channels. So let's say you only have one channel available but 100 users. How will you then allocate resources? So here are some common protocols. The first protocol is the Aloha protocol, where you just transmit as soon as you have something to send. Okay. So again, you have, let's say, an access point. You have different users. They want to communicate with this access point. And as soon as you have something to send, you send it to the access point. Right? And when you send something, you send basically just a short packet. And here it can happen that, well, two users send at the same time, and then they will collide, and then they should retransmit. But when the packets are really short and users don't have to send a lot of data, just sporadically, then this will work, right? Because then you're creating a kind of pattern, very sparse in time with transmissions. There's also slotted Aloha, where you create time slots for these transmissions. And then there's the more common protocol, which is called carrier sense multiple access. Right, and this protocol, well, or one version of this is here. And this operates as follows. So this is running at each device. So each of these nodes connect to this access point. Right, you want to create a frame of data to send. Then you sense the channel. So you listen if someone else is transmitting. If someone is transmitting, then you wait. And you wait a random amount of time and you try again. And at some point, hopefully nobody will be transmitting, and then you can go into this mode, where you first transmit a packet, and these are kind of optional transmissions. This first packet is called request to send. So you send a packet to notify the receiver that you will send something, you send your data. Then the access point should send a packet back called clear to send. Okay? And if you didn't receive this packet, that means something went wrong, and you have to wait again. And this can happen, for instance, because when you send your request to send, someone else was sending something. Or when the clear to send was sent, someone else was sending again something. So then you have to wait. If the request to send was sent and the clear to send was received, then you go on to transmitting of data. And then you are done. Good. And if this request to send and clear to send is not used, then you just, when the channel is idle, you transmit your data. When the channel is not idle, you wait for some random time. And there are many variations of these protocols that are being used. Now, even in cellular communication, when you have communication that is not going on between user and base station, so you could have two user devices and a base station, the communication from base stations to users will be TDMA or FDMA or any of the other MAs that we've seen. But when you have communication between users, then it could happen according to these random access protocols, right? Depending on whether the users are connected to a base station or not. Good, so we covered again a lot of ground where we've talked about uplink and downlink communication, multiple access and random access communication. We've seen mathematical models that unify TDMA, FDMA, and CDMA. You should be able also to list some of their properties. And then we've seen two examples of how to design and analyze multiple access schemes in terms of SINR. So we've seen how to place base stations far enough apart and give the same frequencies when they're far enough apart. And we've also seen how to allocate power to satisfy multiple users. Good, and this ends the lecture on multi-user communication.